So the next topic is called as your voltage divider biasing. Okay, so in the case of voltage divider biasing, the voltage will be divided across two resistors R1 and R2. That's why you have the name as your voltage divider biasing. So your circuit diagram of your voltage divider biasing is given by, so you have an NPN transistor. For stability, you have your RE and CE. Across the collector you have your resistor RC, and across the input side you have two resistors, that is voltage divider resistor, and hence the name R1 and R2. Okay, so input and output will have your coupling capacitor V in, so CC and CC. Okay, so in order for your transistor to act as an amplifier, it has to work in an active region. Okay, so first let us go for your DC analysis. So when we do your DC analysis, your input will be made to 0, your capacitors will be open circuited. Okay, so your circuit will be converted into, you will be having only your resistor, this is your emitter, this will be your base, and your output is going to be a collector. So you will be having your resistor RE across your emitter, RC across your collector, and you have your two resistor, that is R1 and R2 across your base. Okay, input side you will be having only your DC supply voltage. So this is your modified circuit for your DC analysis. So the analysis can be done by two different methods. One is called as your exact analysis, and the second one is called as your approximate analysis. So the exact analysis can be done for all type of voltage divider circuits, whereas your approximate analysis is applied only for which satisfies the specific condition, that is beta RE should be greater than or equal to 10 times of R2. Okay, so first let us see the exact analysis. So in the case of exact analysis, you are going to convert this circuit into Thevenin's equivalent circuit in your input side. Okay, so when I modify this circuit in the input side, how can I get it? So you will be having your emitter resistance RE, from R2 you have your ground, so this is going to be your R2. From the base again you have R1, one end will be connected to your R1 and the other end will be connected to your VCC. So I can redraw it like this. Okay, so this is going to be your VCC. Input side will be redrawn like this. Now this circuit in the input side, I am going to replace it by Thevenin's equivalent circuit. Okay, so when I take the Thevenin's equivalent circuit, this is going to be your VTH, and R1 and R2 will be replaced by RTH. So what will be your Thevenin's equivalent circuit when I replace it by Thevenin's equivalent circuit? By applying voltage division rule, you can get your RTH, your circuit will be converted into RTH, and this is going to be your VTH. Okay, this will be your corresponding current. So this is your current IB. So before that, let me give the direction of the current. So IE is flowing outwards, right? So this towards IE, this will be your IC, and towards your base will be your IB. These are the three currents. So your what will be a value for VTH? This is for exact analysis, first type exact. So your VTH will be given as, VTH will be equal to, when you apply voltage division rule, VTH, the voltage you have to find out across R2, right? So your R2 into your total supply voltage is VCC. So VCC into R2 divided by the total resistors R1 plus R2. So this is going to be your equation 1. What will be your RTH? RTH will be equal to R1 parallel to R2. So this is your second equation. Now if I apply your KVL across your input loop, what will you get? VTH, here it is minus to plus, right? So plus VTH, here it is plus to minus, the current is IB. So take the second polarity, minus IB into RTH. What is your junction voltage? VBE. So here also it is plus to minus. Take the second polarity, minus VBE. So here also it is plus to minus. The current is IE. So minus IERE, which is equal to 0. Okay. So you know that IE is equal to, what will be your IE in terms of IB? Beta plus 1 into IB. So if I substitute this equation, what will you get? So VTH minus IB RTH minus VBE minus, instead of IE you are going to substitute it as beta plus 1 into IB into RE is equal to 0. So now we can take IB as common, right? So VTH minus, if I take IB as common, RTH plus beta plus 1 into RE minus VBE is equal to 0. From this, can we find out the value for IB? IB, I can write it as VTH minus VBE divided by RTH plus beta plus 1 into RE. Okay. So this is going to be your IB. Once you have calculated IB, you know that IC is equal to beta into IB. So what will be your IC? IC will be equal to beta into VTH minus VBE divided by RTH plus beta plus 1 into RE. So you have got the value for your IC. Now if you apply the output loop equation, you will be getting your value for VCE. So what will be your output loop equation? VCC. So here it is plus to minus ICRC, right? Minus ICRC. Here it is plus to minus VCE. So minus VCE minus, again here it is plus to minus IERE. IERE is equal to 0. You know that in terms of IE, in terms of IC is, IE is approximately equal to IC. So if I can group together IC, so RC plus RE. So instead of IE, you are going to substitute it as IC. Minus VCE is equal to 0. So what will be your VCE from this? I can write that VCE is equal to VCC minus IC into RC plus RE. So you have got your operating point, that is ICQ and VCEQ. Okay. So this will be your ICQ, VCEQ. Now let us go for your approximate analysis. Approximate model, you know that it has to satisfy the condition beta RE should be greater than or equal to 10 times of R2. So input side, I can draw the input side, I can reconfigure it into, you will be having your VCC, you will be having your two resistors, right? One is your R1, R2, and across the input you can have an equivalent resistance, that is Ri. And here you have, it will be connected to your VCC. The input side can be reconfigured into this type. Okay. So where you have the value of Ri, have the value for Ri greater than R2. So you will be having the current IB will be very less than your I2. Okay. So I1 will be approximately equal to I2. Okay. So these are the some of the conditions. So this is your main condition, beta into Re should be greater than or equal to 10 times of R2. So what will be your voltage across your base VB? VB will be equal to, apply voltage division rule. So you will be getting the same value, R2 into VCC divided by total number of resistors, R1 plus R2. So this is going to be a first equation, VB. So if I take this circuit, you know that this is equal to VB, right? Now you know that the junction voltage is equal to VBE and here it is IERE. So if you know VB and VBE, can you calculate what is your VE? So VE will be equal to VB minus VBE. In the case of silicon, VBE is equal to 0.7 volt. So once you have got VE, you can calculate IE. IE is equal to, in terms of voltage and resistor, IE is equal to VE divided by RE. So you know that IE is approximately equal to IC. So you have got the value for IC. The output equation is going to be same by applying the output loop equation, VCC minus ICRC minus VCE minus IERE is equal to 0. You know that IE is approximately equal to IC. So what will be your equation? VCC minus IC into RC plus RE minus VCE is equal to 0. So from this, what will be your VCE? VCE is equal to VCC minus IC into RC plus RE, which is equal to that of your exact method. So in the case of approximate analysis, it is more simple. So you are going for 1, 2, 3 equations, finding out what is your VB by applying your voltage division rule, finding out what is your VE. You know, VB is equal to VB is equal to this much. So, you know, junction voltage is equal to VBE, and here this much is equal to VE, right? So, if you know the total voltage VB, VB minus VBE will give you your VE. That's how you have taken this. V is equal to VB minus VBE. Once you know VE, you can calculate IE. IE is equal to VE into RE. So, these are both the analysis. One is your exact analysis and approximate analysis, which will be asked for 12 marks.